Okay, so let us start today's class. So in the last week, we have broadly talked about the routing algorithms that are being used in the internet to forward a packet between two remote hosts. We have looked into two different types of intra-domain routing protocols, distance vector routing and link state routing, and we have looked into the inter-domain routing protocol, which is the border gateway protocol, and that is the protocol that is used nowadays over the internet. Now, for the network administrator within an autonomous system, they have choice of selecting either distance vector routing or link state routing by selecting the corresponding protocol, either the routing information protocol RIP or this open shortest path fast or OSPF, one of the routing protocol. And then at the internet scale, whenever the packets move from one autonomous system to the next, we have seen that we use this border gateway protocol to forward the packets. Now, in today's class, we are broadly going to look into the structure of the routers and how a typical router looks like. Okay, so what are the different components of a router and how a router typically performs. Now, if we see the life of a router, means what the router basically does, that it finds a path, that means it constructs the routing table. Now, once it's constructed the routing table, then for all the incoming packets, it consult with the routing table, find out the next hop and forward the packet. That way it will keep on forwarding the packet. And when there is a change in the routing table, it again find out a path and then again keep on forwarding the packets. Well, so that is basically the route major operations or the kind of life of a router. Okay, so what we see that in a router, there are two basic operations which are being performed. Okay, so one is the constructing the routing table. Well, and the second is once the routing table is constructed, then for every incoming packet, you extract the destination IP address, then do a routing match with the routing table and forward the packet to a dedicated interface based on its next hop information. Now, accordingly, the entire functionality of the router is divided into two different abstractions. One we call as the control plane and the second one we call as the data plane. So the control plane of a router, it basically runs the routing protocol, OSPF or RIP, depending on the configuration by the network administrator. And if it is a kind of BGP configure, then it runs the BGP protocol as well to construct the routing table. So that is the control plane of the router or the control part of the router. Now in RIP or OSPF or BGP, we have seen that it broadcast or unicast different kind of control messages which are the part of the routing protocol. For example, the OSPF hello message to gather the neighboring information. Then in case of BGP to broadcast the NLRI, network layer reachability information. So it basically broadcasts different kind of control packets to gather information about the network and accordingly construct the routing table by running the suitable pathfinding algorithm. Okay, so that is the functionality of the control plane of the router. And the data plane of the router, it basically runs a packet processor, and that packet processor take every incoming packet, extracts the packet headers, find out the IP header from there. Once it finds out the IP header from there, it finds out the destination IP address, and then based on the destination IP address, it does a kind of CIDR match in the routing table and accordingly decide what is going to be the interface to which it is or it will be able to reach to the next hop, and accordingly it forwards the packet. Well, so that is the kind of data plane functionality of a router. Now, based on this control plane functionality and the data plane functionality of a router, we broadly design or we try to do different level of optimizations in a router. So in today's class, we are actually going to look into all those different type of optimizations that typically happen or that are typically run on top of a kind of typical router. Now, if you look into the way this router architecture has evolved over time, so the first generation of the router that were used until 1980s, they were the kind of standard computer. So basically, you connect multiple network interface cards or NICs with your standard computer, and then that computer starts behaving like a router. Okay. Now the second generation router that was in early 1990s, they had the kind of delegation of interfaces. That means it comes with a single unit where it has multiple routing interfaces where you can connect your RJ45 cable and connect multiple different subnets with the router. And at around the same time, the third generation router was also evolved. So this third generation router used to have a kind of distributed architecture. So what is the distributed architecture? Up to the second generation router, this data plane operation and the control plane operation used to happen simultaneously. So you use the same processor to do the data plane operation as well as the control plane operation. So just like a single computer, if you want to use a single personal computer as a router by connecting multiple network interface card, so your data plane operation as well as the control plane operation will get executed in the same processor, right? And the problem of executing the data plane operation and the control plane operation on the same processor is that this control plane operation, it basically periodically broadcasts the routing packets, and based on the information that it observes in the routing packet, it constructs the routing table by running some kind of pathfinding algorithm. Well, whereas the data plane operation, as I have mentioned, its task is to process every individual packet that are being forwarded by this router or that are being routed by this router. Now, that way, if you can think of for a typical router with which I have connected multiple subnets, at the peak hours, I'm going to receive millions of different data packets that I have to process to find out their next hop. Now, if I run or if I use the same processor for the control plane operation as well, then that particular control plane operation also snatches or also uses some computing power. So the remaining computing power gets reduced, and that way the data plane operations become slow. And to make the internet fast, we have to do the data plane operation very fast. You need to process the packet and extract the IP header, do the routing match, and then forward the packet. That means copy the packet to an outgoing interface. This entire process needs to be executed very fast. Okay. So this third generation of the router that contains the distributed architecture, it actually distributes this data plane operation and the control plane operation. So this control plane operation used to get executed on a dedicated hardware calling a route processor. Now on that route processor, it executes the control plane operation. And for the data plane operation, it was basically done or designed in a hardware controlled way, where with the network interface card, you put up a microprocessor, and that microprocessor will do the hardware operation to extract the packet header and then make a match with the destination IP address to the corresponding routing table. Okay, so that was the kind of distributed architecture of the third generation routers. Now the fourth generation routers or early 2000s routers, they were the kind of same third generation routers, but now the size of the router got increased. That way on multiple racks, the routers are being installed. That way the router architecture becomes much more similar to a kind of typical server architecture, where you have a rack, and in that rack you put multiple different servers. So in the same way, in the same rack, type of rack, you put up multiple different routers which are mounted on the rack. Well, and in the today's router architecture, in the direction where we are gradually moving, is the fifth generation of the router that supports a specific type of routing architecture, which is called the software defined routing. So we'll also talk about the software-defined routing in today's class. Okay. Now, if you look into the basic architectural components of a router, this is typically a kind of third generation router where this routing decisions or the routing things are being distributed across multiple microprocessors connected with the interface cards. So we have a dedicated processor for running the control functionalities of the router, which have its own memory and the CPU. So this particular processor is known as the route processor. Okay. And this route processor is connected with the interface cards or the network interface cards or the NICs with the help of an interconnection network. Well, so this interconnection network is an internal of a router which actually interconnects the route processor with the corresponding network interface card. And every network interface card has an incoming interface and as well as an outgoing interface. So through the incoming interface, you receive the data packet, okay, in the form of digital signals. Now, once you are receiving the data packet, the microprocessor which is there attached to the network interface card, it processes the packet. So it is basically a fast packet processor. It processes the packets, it extracts the required information like the destination IP from the packet, make a match with the routing table, and then based on the routing table output, it forward this packet to one of the outgoing interfaces. Right? So that is basically the way this entire router architecture works. Now, as I was mentioning, that is a part of the router hardware. This processor is responsible for control functionalities, and we call this kind of processor as the route processor. It constructs the routing table based on the specific routing algorithm which is being chosen by the network administrator. And then this forwarding is done at the interface card. Right? And for doing this forwarding, one thing you need to keep in mind that this route match needs to be very fast. As I was mentioning, that you are connecting your router to a say GBPS Ethernet, but your router is very slow in processing the packet, then your effective network bandwidth that you will get, it will be very low. Well, because to utilize the 1 Gbps of incoming link and the outgoing link, your router also should be able to process the packets at that particular rate, so that even at the peak hour, there is no stall or there is no edging effect in the entire path. Okay, so that way, this control plane functionalities and the data plane functionalities are basically separated. And for the data plane functionalities, as I was mentioning, that we need this route match to be very fast. And for that particular purpose, we use a kind of special purpose memory management unit, which is called the ternary content addressable memory, or TCAM. Okay, so we'll look into TCAM, that how TCAM is used for doing fast processing of the routing table match and decide about the next hop of a router. Okay, so the internal architecture of the routers is something like this. So you will have a route processor that will run the routing engine, that will run the routing protocol to generate the routing table. And then you will have a packet processor that is basically a microprocessor which is connected to your network interface. And that packet processor will process the packet to decide about the next hop. And depending on that packet processor, the system will actually decide that in which particular outgoing interface the packet need to be forwarded. Okay. Now, as I was mentioning, that from third generation router to the fourth generation router, the basic architectural changes that happened is like you design the router similar to the servers. That means on a rack, you will put up multiple different routers all together. Yes, so here is a kind of example diagram where this kind of large routers, they are built as a slotted chassis. So these interface cards are inserted into the slots and the route processor is also inserted at a slot. And that way you can put up in individual slots, you can put up multiple different routers, and all those routers work collectively for taking the decision or for forwarding the packets. Okay. Now, if I move to the functional component of a router, so as I was mentioning that there are two different planes, the control plane and the data plane. The control plane actually takes care of the routing policies or the routing algorithms that are being used. And the data part or the data plane actually concerned about the forwarding engine. That means how the packets are being forwarded from one how the packets are being forwarded from one interface to another interface. Okay. So now the interesting part is that how control plane actually operates, or how the control plane actually interacts with the corresponding data part. Okay. So in the data part, what we have seen that we need to do per packet processing. So that means if you just think of that your interface supports 1 Gbps link, now in 1 Gbps at the peak hours, you are getting millions of data packets per second, right? And for that millions of data packets, the router need to process. Well, so that way, these IP forwarding rules, it access the routing table, which are actually developed by the control plane by executing the routing functionalities. Okay. Now the control plane on a router. So one thing that I was also mentioning earlier, that a router is a special purpose computer. Okay, so its purpose is to get the packets and accordingly forward the packets to a dedicated interface based on the its own intelligence that it has gathered by running the corresponding routing protocols. Okay. Now this control plane in a router, it is implemented as a software, which is typically the router OS that supports the basic computing functionalities to run a router along with the corresponding routing functionalities. Okay, so the operating system actually embed the different type of routing protocols and their configurations. And as a network administrator, whenever you are buying or procuring a new router, you need to look into its manual and accordingly configure the corresponding protocol as a part of the control plane OS of the router. Okay. So these routing protocols are implemented in the router OS. And one typical example is this Cisco IOS, Cisco Internet Operating System. That is one of the very popular routing operating system that are being used in the Cisco routers. Okay. Now, if you look into the routing functions, there are three different functions that the control plane of a router need to execute. First is to calculate the routes. Okay. So that is the part of the route calculation. Then maintaining the routing table. That means to decide that which are the entries or which entries in the routing table are the stale entries and what new entries need to be added in the routing table. And for doing that, it executes the routing protocol. Okay. Now on commercial routers, routing functions are handled by a single general purpose processor that is called a route processor, as I have mentioned earlier. Now the data plane of a router, it implement the forwarding functionalities, right? So it make a route lookup in the routing table and forward the packet at the destination interface based on the output of the routing table. So the functionality of the data plane of a router is similar to the layer 2 switch. It uses switch fabric. The switch fabric is nothing but a mapping from the input ports to the output ports, or input network interface card to the output network interface card to forward the packet from one interface to another. Well, and every interface maintains an interface buffer to implement the store and forward functionality in a router. So that means once you have received the packet, you process the packet to decide that, well, this particular interface is going to be its outgoing interface, and you put up that details in that particular interface queue, okay, or the interface buffer. Okay. Now, this IP forwarding, as I was mentioning, that we need to do per packet processing of the IP packets, and this is a kind of very heavy task. you need to do it very fast. Well, so this IP forwarding is distributed. It is handled by individual interface controller. So the individual interface controller actually process the incoming IP packets and accordingly decide what is going to be the outgoing interface for that IP packets. And to make this entire decision algorithm, that means making a CIDR match with the routing table, we use a special hardware device which is called a TCAM, ternary content addressable memory. So here is a kind of diagram that actually explains this per packet processing in a router. So you will have a routing table.
Sir, you are not audible.
Hello. Sir, you are not audible.
Okay. Now coming to this concept of forwarding information base. Well, so
Sir,
as I have,
hello.
yeah, any
Sir, right
query?
from the start of the last slide, you were not audible.
Which part?
Sir, right from the beginning of this slide, when you started explaining, uh, you were not audible.
Okay, good. So, okay, so let me repeat this part. So, as I was mentioning that we have multiple different interfaces, and for every individual interfaces, I take the decision, packet forwarding decision as an independent way. That means when a particular packet reaches to one of the interface, that interface will make a match of the destination IP address with the corresponding routing table to decide what is going to be the next hop and what is going to be the outgoing interface to forward the packet to the next hop. Now, how we are going to do that? For that, actually, we take the global routing table. So this is the routing table that is being constructed by the routing protocol. So a part of the routing table is actually copied in the memory of the individual interfaces. So we cannot copy the entire routing table because of the space constraint, because for a large scale router, the size of the routing table is also large. That's why you do not have the flexibility to copy the entire routing table to an interface. So you copy a part of it. Now, whenever you are copying a part of it, that particular thing is called a forwarding information base that we are going to talk in the next slide. Now, in every individual interface, whenever you are receiving an incoming packet, so assume that you have received an incoming packet in this interface. Now, once you have received an incoming packet to this interface, then it will extract this interface packet processor. It will extract the IP header from the packet. Then it will look into the destination IP address. Now, once it looks into the destination IP address, it makes a match with the routing table or a part of the routing table that is available in the interface card to decide about where is the next hop. Accordingly, once you get the next hop information, you copy this to an output buffer. Now, the remaining part works like a layer 2 switch. So what typically happens that from the output buffer, whenever you are picking up a packet, you see that based on the routing decision, what is going to be my next hop. And for that next hop, in which particular interface, I need to copy the packet. So the packet is through this switch fabric, the packet is copied from the input interface to the corresponding outgoing output interface for scheduling the output of the packet. Okay, so that are basically the steps which are being executed. Now this entire process, one thing that I have mentioned that this entire routing table you cannot copy. Okay, so you basically copy a part of the routing table to a network interface, and that part is basically called a forwarding interface, forwarding information base or FIB. Right. So that way, every network interface card, the interface of an FD network interface card, it maintains a forwarding information base that is a mapping from the input interface to the output interface based on the output of the routing table. So a replica of the routing table is used at the interfaces for making the forwarding decision. So the entire steps are as follows. So you have an input packet that is being marked by the packet in event. So the packet is put in the input interface. So you extract the packet, process the packet, find out the destination IP address from the IP header. Now, once you are reading the destination IP from the IP header, you make a lookup in the forwarding information base. Now, as I was mentioning that there can be this forwarding information base is actually a part of the entire routing table. So that way it is highly possible that the information that you are going to look up into FIB, it is not available there. So you have a FIB miss. So if you have a FIB miss, then you make a route lookup. Okay. So that route lookup actually looks into the original routing table and you fetch that entry and put it in as a part of your FIB. So here you can see that FIB basically works like a cache for the routing table. Okay. Now the routing protocols are used for generating that routing table. Now, if you have an FIB hit, that means you can find out an entry in the FIB. Then based on the outgoing interface, you forward the packet, that means copy the packet from the input interface to the output interface. So that is the kind of entire steps or the different steps which are being executed when our packet is being forwarded through a router. Okay. So any doubt up to this point? Okay.
This FIB lookup is fixed or updated dynamically?
This FIB lookup is updated dynamically. Dynamically in the sense depending on, so you can just think of or kind of match the behavior of FIB with the behavior of a typical cache. Okay, so typically in a cache that you make a cache lookup, if the entry is there in the cache, you have a cache hit and you process it. And if it is not there in the cache, then you get the entry from the main memory. The same thing happens here. The original routing table or the complete routing table is put up in the main memory of the router. Okay, and the memory or the cache of every individual network interface card, it contains a part of that routing table that we call as the FIB. Okay, so and that way the FIB might not have the complete entry, and because the FIB do not have the complete entry, there might be an FIB miss, and if there is a FIB miss, you do a route lookup through the software and fetch that entry to the FIB. Okay, so remember that FIB lookup is actually implemented in the hardware, so that TCAM hardware ternary content addressable memory that I have mentioned. We are going to look into that details, that how that is being processed in the hardware. and it is processed in the hardware particularly because this processing need to be very fast. If you going to do a kind of software processing that is typically done in the route lookup part, when there is a miss in the FIB, that takes time. Okay, but doing a kind of fast processing, you do it in the hardware, so that is done within the FIB. Okay, any other doubt or any other query? Okay. Now, that way, typically in a router, we use these two terminologies, routing information based and the forwarding information based. So the routing information base is the original routing table that is implemented in the software and is maintained by the control plane of the router. And the forwarding information base of the FIB is the copy of the required routes that is maintained in the network interface card within the TCAM hardware. Okay, so this RIB is dynamic and it maintains the entire routing information, whereas FIB is updated whenever required. So if you are having an FIB miss, then you basically fetch a new entry from the RIB to fill it up in the FIB. Okay, so in the same way or in the same policy that we typically use in case of design. Okay, so here is some kind of example. So a router has this complete routing table, that is the routing information base. Now a part of it, I put it in ETH0, one interface, and the part of it, I put it in ETH1. So the part which are there in ETH0 and ETH1, they are the kind of forwarding information base of the FIB. Okay, so it is the part of the entire routing table. So you see that all the 4 entries are not there. So the FIB at ETH0 contains 3 entries and the FIB at ETH1 contains 2 entries. So depending on the packets that are being encountered at every individual interfaces, it updates its FIB accordingly. Okay, so if a packet has been accessed or processed very recently, then that entry is there in the corresponding FIB. And the idea is something similar to the caching idea, that if you are going to see a packet for a particular flow, you are likely to receive more packets of that flow. Okay, so it works on this principle that once you get a new packet for a new flow and say the entry is not there in FIB, you do a route lookup and fetch the entry from RIB to FIB. Then it is not like that an end-to-end network flow will only contain a single packet. It will contain multiple packets, and sometimes it is of millions of packets that are being forwarded. Okay, so that way this caches are maintained within the individual network interface card. So that way, this RIB, it actually feeds the FIB. So we will have multiple different routing table in the control plane. We can have static routes. We can have the routing table corresponds to SPF, that is the link state database for doing the intra-domain routing. Then you have the BGP4 routing table. So this BGP4 routing table is the routing table for inter-domain routing. Well, and all these different entries are fed into the routing information base, or it populates the global routing information base, and then the part of it is being taken at the forwarding information base at the forwarding table. Fine. So that is the kind of entire end-to-end architecture. Now coming to the basic TCAM architecture. So this TCAM actually works in this way. So as I have mentioned that it is a specific type of hardware for doing a route match, ternary content addressable memory, so that you can process the routing decision in the hardware itself. So here I will just try to explain it with the help of an example. So here are 4 different entries and how these entries are designed. So if you look into the packets, for example, for the time being, just assume that your IP addresses are 4-bit address. Okay, typically it is a 32-bit address. Just for the explanation purpose, assume that it is 4-bit. Now in this 4-bit, if I just define as a IP subnet in the CIDR notation as 101/3, that means my network IP is 101 and the fourth digit I do not care, right? Because whenever you are doing a kind of ANDing with the subnet mask, so that particular bits in the subnet mask are 0, and if you are doing a logical AND with something with 0, it will always come 0. So that's why in my input IP, whatever be there in the host address part, that becomes my don't care condition. Okay. So if your CIDR notation, the address is 101/3, then in TCAM format with 4-bit, it becomes 101x. Okay, but the last bit is don't care. Similarly, if it is 1113, it becomes 111x, 10/2, it becomes 10xx, 0/0 becomes xxxx. Well, now these entries are put in the TCAM hardware. So the lower entries are the xxx, then 10xx, then 111x, then 101x. Now assume that you get a packet and the destination IP is 1010. Okay, and you want to make a match. Well, so your first bit is 1. So once your first bit is 1, you get a match. Okay. In the second entry, you also get a match. In the third entry, you get a match. Your fourth entries don't care, so you also get a match here. Well, now let us process the second bit. For the second bit, it is 0. You get a match to the first one. The second one, that is a mismatch. And the moment you are getting a mismatch, that particular line is blocked. So that particular line is not needed anymore. Then for the remaining 2, there is a match. The third bit is 1. For the third bit, for the second one, I don't want to check anymore. Okay. So for the third one, I have a match in 1, 3, and 4. For the fourth bit, I also have a match in 1, 3, and 4. So I have a match in 0, 0, 1, 0, and 1, 1. Okay. Now this particular encoder, it will actually take the match where longest number of bits have been matched. Okay. So whenever you are taking the longest number of bits that have a match, so the last 2 entries were kind of XX. They are the kind of don't care condition. And the longest match I had in the first entry where I had matched for 3 different bits. Okay. For the third one, I had the exact match for the 2 bits. Well, then we had the, so that way, if we consider the don't care and accordingly find out that where is my longest match is in the first one, then the first line is selected and that line is being forwarded as my output. Okay. So this way in the hardware, the packets are being processed and this processing is very fast because you are processing in the hardware. Well, and that way actually your route lookup becomes very fast with the help of this forwarding information base that you are putting in the format of a hardware rule rather than a software rule, and then forwarding the packet. Okay. So that TCAM hardware is actually used in the network interface card. And basically, so earlier we had a kind of query that why do we typically use both L2 switches and routers? Why not replace all the L2 switches with routers? Now, typically in the routers, because the router need to do this route lookup and a match with the table, and to match with the table, we need this TCAM hardware, which is very much costly, and because of which routers are much more costly compared to a layer 2 switch. Okay, so that's why whenever we are designing a network, we design it in that way. So if I first try to create a layer 2 subnets, well, such that I put all the machines in the same subnet, and then whenever you are going out of the subnet, you connect it with a router. Sorry. So that is the entire processing that are being done to forward the packets in a router. Okay, any doubt up to this point? Okay. Now let us broadly look into this idea of software-defined networking, which is actually the 5th generation router, and currently the routers which are coming to the market, they utilize this concept of software-defined networking. So the idea of this software-defined networking is basically to separate out the data plane and the control plane of the router. Now you see this control plane of the router is actually the main overhead for a router. Well, because these typical routers work in a distributed fashion and the routing algorithms are also distributed, because of which we have seen that we had count to infinity problem and so on. So that's why the idea is that let the data plane be there in the router, well, and the control plane take out of the router and make it a logically centralized control plane. So that is the kind of core idea of software-defined networking. So the software-defined networking is a network framework which involves in separating a network's control function from its data forwarding functions, centralizing its intelligence and abstracting its underlying architecture from applications and services. So the core part of the software-defined networking is that you separate out the control plane and the data plane of a router. The data plane of the router, it is typically implemented in the hardware and let it be in the hardware. Whereas the control plane of the router, which is implemented as a part of the software, you put it as a kind of central controller within an autonomous system and make this control functionalities logically central. Okay. Now, if you can make the control functionalities logically centralized, your advantage is that you will not land up with the standard problems like counterintuitive, because from a central controller, you are going to take the decision about constructing the routing. Now, as I was mentioning, that the control plane of the router is the module which takes all the decision basically and instructs it basically runs the routing algorithm. Whereas data plane is the module which carries out the task given by the control plane. So it task is basically forwarding the packets by looking into the routing table and finding out a routing. Now, in traditional networking devices that are the kind of proprietary device, they are typically the vendors, they decide the software. That means the control planes are decided by the vendors. As I was mentioning that in case of Cisco routers, they use Cisco iOS or Cisco Internet Operating System as a part of their control plane. And that means there is no standardization of the control plane. That means different vendors use their own optimizations in the control plane and the software part. And that way the development or the R&D is somehow disconnected, because individual companies or individual enterprises, they build up their own system that they keep as the proprietary. So that way, in a typical router, this control plane and data plane are actually tied together, and there is a kind of strong interconnection between them. Right? Now, why we typically want to separate the control plane and the data plane? Because this control plane, we want to make it logically centralized, and we want to make it a place for open innovation, so that anyone can design a new routing algorithm, or anyone can decide their own routing policy and put it up in their control plane. Okay, so that way, with the idea of the software-defined networking, the vendors only provide the hardware, which is the data plane, and we decide the control plane by writing custom logic within the software. Now, the advantage of such kind of architecture is that the features are no longer limited to what the vendor provides. You can build up your own feature within the open source control plane, and it helps in community development of new protocols and a longer life of the product. That is the standard things of a kind of open source idea. Okay. Now, how SDN work? That compared to the traditional network, software-defined networking has two types of device. One is the software controller that contains the
Sir, you are not audible again.
So I guess that I got disconnected. Am I audible now?
Yes, sir.
Okay, got it. So there was some problem in the IIT network. Suddenly I found that the network got disconnected. So let me connect, clear the slides and quickly complete the concept that we are talking about. Yeah. So yeah, we are talking about this kind of SDN architecture. So this layer 2 switches, they work like a kind of dumb device that are just having a kind of forwarding logic embedded in it. Okay, so let me explain with an example that how this controller to switch coordination work. Now this SDN controller is the kind of brain of the network. So all the policies, routing logic, everything are placed in the controller. Okay, and it teaches the switch about what to do with an unknown packet. So here is an example. Say, let us see a scenario where a packet wants to go from H1 to H3 in an SDN environment. So I send a packet from H1, it reaches to the switch S1. So the source is H1, destination is H3. Now, initially there is no routing rule in S1. Well, so there is a FIB miss because I do not know that what to do the packet. In that case, S1 basically contacts the controller. Okay. So based on the control logic, the controller generates the rule based on the software programming, and that is the routing logic. And the controller informs the switch that what is going to be the rule. And that rule is installed in the switch 1. Now, once the rule is installed in the switch 1, the packet which was buffered in S1 that is forwarded to H2. Well, so that is for the first packet. Now for the next packet onwards, you already have the rule in S1. So the packet reaches to S1 and it is being forwarded to H3. So that is the kind of broad idea of an SDN network, that you separate out this control plane from the switches or from the routers, put it in a centralized, logically centralized location, maybe a kind of server or a machine with which all the different switches are interconnected, and you run your control logic on top of that particular controller. Okay, so there are multiple commercial controllers available which supports based on one typical protocol which is called the OpenFlow. So that OpenFlow controllers are available, and that OpenFlow controllers, there you can put up your custom logic for this forwarding rule installation and all these things. Right? And accordingly, the router switch comes to the market, that is only the hardware. It does not contain any rule, and dynamically these rules are placed depending upon the control logic. Now, in SDN, basically we have these 3 layers currently. So we have the programmable switches, which is my infrastructure layer, the hardware. On top of that, I have a network controller that actually is the brain of the entire network. So I am separating out this controller and making it logically centralized. In the traditional architecture, this controller was a part of the router, and that way it used to run the distributed protocols like RIP or OSPF. With the SDN architecture for an intra-domain routing, at least I do not need to run that kind of centralized, that kind of distributed algorithms like RIP or OSPF. Within the controller, I can embed the logic, and that logic can be installed in every switches. Okay, and on top of that, different network applications can run altogether. Well, so that way, if you look into the difference between the traditional network architecture and the SDN architecture, in case of traditional network architecture, it used to have a distributed control plane where the control plane was embedded with every individual data planes. Now we are taking the control plane out and making a logically centralized. Okay, and the data plane is still distributed. Now this kind of idea is gradually becoming popular, and currently all the large scale network like the Google data center or the Facebook data center, they already use these software defined routers or the software defined switches. Even in a lower scale, so for example, within IIT Kharagpur network, I know that there is a discussion going on whether we are going to replace all our routers with SDN supported routers or not. So what you can expect that within the next 5 to 10 years, all the routers are going to be replaced by such kind of software-defined routers. Yeah. So within the next 5 to 10 years, you are going to see that all the different routers are going to be replaced by software-defined routers. Okay. So this is something all about the structure of the routers. And in the next classes, we'll talk about few of the control protocols which run at the IP layer, and then we'll move towards the MAC layer. So any doubt up to the topic that we have covered in today's class? Any query or question? Okay. So before I close, just an announcement that we'll have 2 more class tests. Okay. One, the first, so from the part that I am covering. So one class test will be on this weekend. That means on March 27, Saturday, using the same formalities that RSC used to have. So yeah, so we'll have one class test on this Saturday using the formalities that RSC used to have from 4 p.m. to 5 p.m. And the last class test we'll have sometime near the end of the course, maybe in the second week of April, that I will announce. So for this first class test that I will going to take on this Saturday, that means on March 27, the syllabus is the IP addressing and the routing. Okay, whatever we have covered till last class, not for today's one. Well, so that will be the part of the syllabus. So any query regarding that? Okay, fine. Then we are again going to meet tomorrow morning.
Sir?
Yeah, Shumam.
Sir, yeah, in the software-defined network SDN you are saying, so is it not a problem to have the control plane totally centralized? Because if somehow the computer that is giving the control instructions that goes down, then the whole network will switch off, right?
Right. So you are right. So that's why typically, so I have not gone to the details of this architecture because of this timing constraint and all these things. Typically nowadays it is covered in an advanced networking course. So
Sir, I think you are not audible.
sorry, so there is not of network glitches today, it seems. Anyway, so let me just answer the query before I leave. So yeah, that is typically a problem if you are going to use a single controller. Now, in a standard approach, what we typically do that we also put up a backup machine that runs as a controller, typical to any kind of servers, where if the primary controller goes down, then the secondary controller takes care of it. But yeah, it is a kind of real problem, but people are working towards that. So even people are thinking about to have kind of distributed controller for large scale network. But yeah, this SDN idea of SDN that has been designed till now, it is to operate within a single network, like a kind of single autonomous system. So within a single autonomous system, if we have a primary controller and a backup controller, that will suffice. Any other query? Okay, if not, then thanks. So we'll be starting tomorrow with a kind of few network control protocols like ARP, DHCP like that, and then we'll move to the data linking. Thank you, everyone. See you tomorrow. Take care. Bye bye.